Hi guys, this is a fourth problem we are solving on the trusses. In this problem, if you have a look at it, so in the problem he is clearly asking us to find out the reactions. Okay, so determine the reactions. As we all know that if you want to find out the reactions or if you want to find out the stresses, whatever it might be, our first aim is to find out the nodal displacements. Okay, well, if I find out the nodal displacement, I can find out the stresses, even I can find out the reactions. Okay, so look at this problem. So here, this problem is, if you just have a look into it, previous problem where we have solved by taking all the dimensions in meters, but here he has given every dimensions in terms of mm. Okay, 4000 mm, 3000 mm, and the area is also given in terms of mm. Okay, now he has given Young's modulus as 200 GPS. So since everything is kept in mm, so I'll keep this Young's modulus also in terms of mm itself. So 200 into 10 to the power 3 megapascal or Newton per mm square. Okay, as usual, first what we need to do is we need to create a finite element model. So what I'm going to do is, okay, at the junctions, at the ends, I'm going to place the nodes. So if I place the nodes, okay, see, these are the three possible nodes what I can place. So this is your node number, give your node numbering in your counterclockwise direction. So node number 1, node number 2, and this is node number 3. Okay, now also I'm going to go over the element numbers also in counterclockwise direction. So this is element number 1, this is your element number 2, and this is your element number 3. So what I need to do is I need to take my extreme left bottom as my origin. Okay, so if you move in this direction it is x, and if you move in this direction it is y. So this is where I'm going to place my coordinate system or my reference system. So when I'm going to place my reference system, the coordinates for your node number 1 will be 0, 0. From the origin, in order to reach node number 2, you're going to travel only in your x direction. So that is why x is 4000. Since you're not going to move in y direction, so y value will be 0. Now from 1 to 3, you're going to travel first along x direction by 4000, then you're going to travel y direction by 3000. So 4000 comma 3000. Okay, so this is a major thing what you need to understand. So 4000 comma 3000, this is your coordinates. Once you have got this, so once you have spent this time at this point, okay, now we need to form a nodal data. So you're going to write the node numbers. How many nodes are there? 3 nodes are there. Node number 1, node number 2, node number 3. What is the value of x and y? For node number 1, x is 0, y is 0. For node number 2, x is how much? 4000, y is 0. For your node number 3, it is 4000 comma 3000, 4000 comma 3000. Okay, I'm keeping every dimensions in terms of mm itself. Now we know that element numbers, how exactly I've given the element numbers in a counterclockwise direction. So you have to club 1 and 2. So since you're going in anti-clockwise direction, so you are here. So initial node for your element 1 is 1, and where exactly it is going to end, it is at node number 2. Now you are at this location. Node numbering for your element 2, initial node is 2, final node is 3. Now you are at this location and you are moving in anti-clockwise direction. So this for your element 3, this is your initial node and this will be our final node. So 3 and 1. Okay, see, look at this. In is nothing but initial node, fn is nothing but the final node for that element. Okay, what are the coordinates? See, in the from the table you can look into that coordinates 0, 0. For node number 2, what are the coordinates? 4000, 0. For your node 2, what are the coordinates? 4000, 0. What about this one? For this node number 3, it is 4000, 3000. So meanwhile, for your node number 3, it is 4000, 3000, and for your node number 1, it is 0, 0. Now, what is this LE? LE is nothing but the length of the element, and L and M are the direction cosines. We know that the length of the element is given by the formula, okay, xf minus xi the whole square plus yf minus yi the whole square. Okay, now for the length of the element 1, okay, look at the diagram. No need of going with this calculations at all. If you want to do the calculations also, it's fine. Look at this. He has given the distance between 1 and 2 as how much? 4000 mm. So the length will be obviously 4000 mm. If you do the simplification also, you're going to get the same answer. And meanwhile, look at your element number 2. Element number 2, the length is given as how much? 3000, or in other words, the distance between 2 and 3 is given as 3000. So that is nothing but your length of the element, 3000. Okay. For your element 3, you need to go with this calculations. If you do the simplification, for your element 3, you are going to get 5000. Okay. Yeah, 5000 mm is your length of the element. And what is a direction cosine L? L is equals to, the formula is which is nothing but equal to cos theta, which is equals to xf minus xi divided by length of the element. Okay, if you try to calculate L1, and this where 1 indicates for element 1, and L2 is for element 2, and L3 is for your element 3. So xf, now come to element 1. Xf is how much? 4000. Xi is how much? 0. 4000 minus 0 divided by 4000, you're going to get 1. L2 also, you just look into it. See, xf is how much? 4000. Xi is how much? 4000. So 4000 minus 4000 is 0. 0 divided by 3000 is 0. Now look into this L3. So xf is how much? 0. Okay, I'm going to go with this formula. 0 minus 4000 divided by length of that element is 5000. If you do the simplification, you're going to get as minus 0.8. Okay, now write these values, all this. See, this is for element 1, this is for element 2, and 0.8 for element 3. So 1, 0 minus 0.8. Now we know that m is equals to sine theta, which is equals to yf minus yi divided by length of the element. Okay, now so for your element 1 it is m1, for your element 2 it is m2, for your element 3 it is m3. So now come for your element number 1. Here is data. Yf is how much? 0. Yi is how much? 0. So 0 minus 0 divided by 4000 is 0. Okay, write that value. Okay, meanwhile m2, look at this. How much you have? 3000 is a yf value, because that is yf for your element 2. 3000 minus 0 is 3000. 3000 divided by 3000 is 1. Okay, if you want it, I'll show the calculation. See, yf is 3000, yi is 0, all divided by 3000, where you're going to get 1 as your answer. Now come to your m3. Be careful. See, this is your yf. Yf is how much? 0. Okay, yi is how much? Sorry, yi is how much? 3000 minus 3000, all divided by length of element is how much? 5000. How much you're going to get? If you do the simplification, you're going to get yf minus yi. Minus 0.6. Okay, minus 0.6 is your answer. Now, so if you just do the simplification, m1 is 0 for element 1, 2 subscript is for element 2, so you are going to write 1, and for your element 3 it is minus 0.6. Okay, minus 0.6 is the answer. Now L square is 1, M square is 0, Lm will be also 0, because 1 into 0 is 0. Now do the simplification. L square is 0, square is 0, M square, 1 square is 1, L into M, 0 into 1 is 0. So L square is minus 0.8. L is minus 0.8. L square is 0.64. Now M is 0.6. M square is 0.36. Now L into M, 8 6 are 48. Minus into minus becomes plus 0.48. So this is how you are going to prepare your element table data. This is the major thing what you need to do. Once you are done with this, next we are going to go with once you are done with all this data, our next intention is to find out the stiffness matrix. We know that the stiffness matrix formula is given by AE LE by L square LM M square. So if you write the first part, it is sufficient. Okay, if you write the first part, it is sufficient, because the same negative values. Okay, See, this is a positive value and this is the negative value, so you can write it. Okay. Now, since we have three elements, we need to individually find out A1, E1 by L1, because if you do this, you can reduce your calculation steps. Okay. So A1, E1 divided by L1. So area 1 is given in the question itself, that is 200 mm square. So this is 200 and Young's modulus is 200 into 10 power 3. Length of the element 1 is how much? That is 4000. Where is that? Okay. Now look into this. So this is your length of the element 1 is 4000, length of the element 2 is 3000, length of the element 3 is 5000. So 4000, and this is for your element 2 3000, and this is for your element 3 5000. Okay, because numerator is same, because area is 200 200 200 for all the three elements is made up of same area and same material. So so the numerator is not going to change, only the denominator has been changed. If you do the simplification, you are going to get 1 into 10 to the power 4. Okay, if you do the simplification, you're going to get 1 into 10 to the power 4. Similarly, you do the scale simplification, you're going to get 1.33 into 10 to the power 4. Meanwhile, when you do it for your element 3, you're going to get 0.8 into 10 to the power 4. Okay, now look into this. Now, by using my element table data, I'm going to form this elemental stiffness matrix for your element 1. See, in your element 1, you have only L square. M square and Lm is 0. So L square is 1. Lm will be 0. M square is also 0. So if I write it 1, 0, 0, 0. Now the same values, but with a negative sign, will be written in the next part. Okay, and the same negative part will be replaced here. And this is a positive part. Now here, if you look at it, what is the value we have got? AE by LE is 1 into 10 to the power 4. So what I would have done is, I've kept my 10 to the power 4 common, and if you multiply 1 with this inside the stiffness values, you're going to get the same answer. So I'm not going to bother much about it. Now let us come to element number 2. Yeah, when you come to look at this, this is element number 2. From your element table data, you can see that L square is how much? 0. M square is how much? 1. Lm is 0. So L square is 0, Lm is also 0, Lm is also 0, M square is 1. So 1 will be there. If you multiply, see, since what I've got, when you multiply A2 E2 by LE2, you are going to get 1.33 into 10 power 4. So I have kept 10 power 4 common, and I have multiplied 1.33 with the stiffness values inside the bracket. So you're going to get plus 1.33, minus 1.33, 0, minus 1.33, and plus 1.33. Okay, now let us come to for our element number 3. So L square is 0.64, M square is 0.36, and Lm is 0.48. So L square is how much? 0.64, Lm is 0.48, and here also you're going to get 0.48, and M square is 0.36. Now what I've done is, see, when you multiply A3 E3 by LE3, you're going to get 0.8 into 10 to the power 4. Now I'm going to multiply this L square with 0.8 inside the stiffness values, and 0.36 also with this 0.8, and 0.48 also with this 0.8, which was obtained like this. 10 power 4 is kept common. So if you multiply 0.64 with 0.8, you're going to get 0.512. If you multiply 0.8 with 0.36, you're going to get 0.288. And if you multiply 0.48 into 0.88, you're going to get 0.384. The same values with a negative sign is written on the right side, and the same values with a negative sign written on the bottom, and the positive values will be written in the next part of this. After this, now again I'm going to come to the diagram. Okay, this is very much important. Now at node number 1, how many degrees of freedom we have? Since this is a truss, you have a coordinate system x and y. So you're going to get two displacements, one along x direction and one along y direction. Okay. So meanwhile here also you're going to get one displacement along x direction and one displacement along y direction. So this is your q1. If you move in this y direction, q2. If you move in this direction, x direction, q3. If you move in this direction, q4. And along x direction, q5. And along y direction it is q6. And meanwhile I'll represent the force. The displacement occurred at q1. The responsible force is F1, and the responsible force is F2. And for the displacement of q3, the responsible force is F3, and for your q4 it is F4, and for your q5 it is F5, and for q6 it is F6. Why have I written this? because this is necessary for me, the degrees of freedom, because in order to form the global stiffness matrix I need the degrees of freedom. Now look into this. For your element number 1, you have a degrees of freedom 1, 2, 3, 4. Okay, now I'm going to write that one. 1, 2, 3, 4. 1, 2, 3, 4. In spite of writing Q1, Q2, Q3, Q4, I have written 1, 2, 3, 4. So whichever the way you want. For your element number 2, what are the degrees of freedom? 3, 4, 5, 6. In the same sequence, you're going to start the same sequence. 3, 4, 5, 6. In spite of writing Q3, Q4, Q5, Q6, I am writing 3, 4, 5, 6. Okay, once you have done this, next for your element 3. Now, this is where you need to be. See, you are moving in a counterclockwise direction, so that's what I told. For your element 3, this is your initial node. So you're going to start with 5, 6. Then you're going to come up with 1 and 2. Okay, 5, 6, 1, 2. So 5, 6, 1, 2. Okay, so this is how we are going to form a individual element stiffness matrices. Now our intention is to form the global stiffness matrix. How many degrees of freedom we have? 1, 2, 3, 4, 5, 6. Totally 6 degrees of freedom we have. So 6 degrees of freedom we have. The global stiffness matrix. If you look into all these matrices, the order is 4 cross 4. This is also 4 cross 4. This is also 4 cross 4, and this is also a 4 cross 4 matrix we have obtained. Now we are going to form a global stiffness matrix whose order is 6 cross 6. Okay, so how am I going to form that global stiffness matrix? It's very simple. Look into this. Now this global stiffness matrix will be formed. Okay, now write all the degrees of freedom, that is 1, 2, 3, 4, 5, 6. Q1, Q2, Q3, Q4, Q5, Q6. Q1, Q2, Q3, Q4, Q5, Q6. Now look at this one. Now how are you going to form this one? You need to read it as, in spite of degrees of freedom, you can read this as a first column, first row. What is the first element? You have 1. Okay, meanwhile, look into this. Search your stiffness matrix. Is there any value, stiffness value, which is going to sit in the position 1 and 1? Okay, yes, there is one more value. So from this is a 0.512 and 1. Okay, if you try to add it, see 1 plus 0.512. So I have written the value already. So 1.512. Next, second column, second row, what do you have? 0. But look into this. Second column, second row, what do you have? It is 0.288. Okay, so sorry, I have done a mistake here. So this is 0.288. It is 0.288. And now come to third column, first row, what do you have? -1. Fourth column and the first row, what do you have? 0. So I have written that value. See, -1 and 0. Now we're going to come for fifth. See, what you need here is fifth column, first row. What is, there's something to be filled. So fifth column, first row, you have -0.512. I'm going to write that -0.512. Now as usual, in the sixth column, first row, what do you have? Sixth column, first row, you have -0.384. I have written that value. Once you have got a row, you can replace the row with the column, because that is a property of your stiffness matrix. 0.288 -1, and this is 0. Yeah, -0.512 and -0.38 -0.384. Once you have written the column, so once you have written the row, the same values, leaving this, whatever the values is there, you can represent it in a column. Now come to this one matrix, 2 cross 2. Okay, in the second column, second row, what do you have? 0. So here you have 0. But let me look into the other matrix. You have 0.288. Okay, sorry, this is 2-1. I think I made a mistake. This is 0.384 was correct. Second row, first column, it is 0.384. Sorry. 0.384. Sorry for that. 0.384, 0.2880. Like this, if you try to form a stiffness matrix by looking at the values. Now see, I've done the second row also. 0.2880 minus 0.384 minus 0.288. Now the first row will be replaced by, second row will be replaced by the second column. 0, 0, minus 0.384 minus 0.288. Like this, if you just try to look into the matrix carefully, you can form the global stiffness matrix. Okay, 1 0 0 you have next I'm going to replace 0 0 0 over here. 1.330 minus 1.33, 0 0.512, 0.384 minus 1.33 and 0.384. Okay, this is how you are going to form a global stiffness matrix. Okay, you need to look into this three stiffness matrices and you're going to form a global stiffness matrix. And out of this, all the three, which is a common, 10 to the power 4 is common. So that 10 to the power 4 is being written over here. Next, what is the next thing? Okay, once you have formed a global stiffness matrix, next thing is to find out the global force vector. Okay, now the global force vector, again you need to utilize the diagram carefully. Okay, if you want to utilize the diagram carefully, see Q1, the displacement will be happening due to force F1, F2, F3, F4, F5 and F6. Now look into this. At node number 1, is there any force acting along this Q1 direction? No force. Along Q2 direction, is there any force acting? No. Along at node number 2, is there any force acting along F3 direction? No. And along the F4 direction also, no force is acting. So F1 is 0, F2 is also 0, F3 is also 0 and F4 is also 0. But let me come to node number 3. But look into this. Here you have a force which is acting along the Q5 direction, that is, it is on the positive direction, so it will be plus 15 into 10 to the power 3 Newton. Now look into this 20 kilonewton which is acting along the Q6 direction, but it is moving in the opposite direction. Okay, so opposite direction, or in other words, it is acting in the negative y direction. So this is positive y. When you move in the upward direction, it is positive y. When you move in the downward direction, it is negative y direction. So I'm going to write that minus sign, 20 into 10 to the power 3 Newton. So our next step is to form the global equilibrium equation, which is given by K into Q is equals to F. Okay, I've already written that. If I try to write that, you are going to get like this. So this is your stiffness matrix, global stiffness matrix, and this is your global displacement matrix, and this is your global force vector on global force matrix. Now, how are we going to apply now we need to apply the boundary conditions. So we are going to apply the boundary conditions by elimination method. Okay, we're going to apply the boundary conditions by our elimination method. Okay, so again, utilize the diagram carefully. See here, you can see it is completely fixed. Node number 1 is completely fixed. So that means when it is completely fixed, there will be no displacements along x and y direction. So that is Q1 and Q2 will be equal to 0. Now let us come to node number 2. In node number 2, he has given the roller, means it is free to move along x direction, but it is supported along y direction. Okay, so here Q4 will be 0. Okay, so Q1 will be 0, Q2 will be 0, Q4 will be 0, because it is completely restrained along that directions. Okay, along y direction it is completely restrained. Along y direction, what is the displacement? Q4 is my displacement, so which will be completely restrained. And similarly, Q1 and Q2 is completely restrained. So by elimination technique, okay, if I apply boundary conditions, I am assuming that Q1 is equals to Q2 is equals to Q4 is equals to 0. So now what I need to do is I need to eliminate. See, look into this. You're going to look at the subscripts, which are the terms I have taken 0, 1, 2 and 4. So you need to delete first row first column, second row second column, fourth row fourth column. Now I'm going to delete my first column and my first row. I completely deleted that. Okay, next I'm going to delete my second column and my second row. See, I completely deleted that. Next one is fourth column. I deleted that, and wherever is the fourth row, I have deleted that. Now we have left out with, see, we have left out with 1. I've written that 1, 0, 0, 0, 0, 0, 0. I've got it. 0.512, 0.384, 0.512, 0.384, and 0.384, 1.618, 1.618. I have written those values. Okay, now you're going to come across here in this column, in this matrix, we have left out with Q3, Q5, and Q6. Here you have 0, 15 into 10 power 3, minus 20 into 10 power 3. So those are the values we have obtained. If you solve this matrix by simultaneous equations method, okay, you are going to get the values of Q3, Q5, and Q6, which you can solve in your calculator. So Q3 is 0. Q5 we have got 4.619 millimeters, and Q6 is minus 2.349 mm. Whatever the answer we have obtained, that is in terms of mm. Okay, so once we have obtained all these values, our intention is to find out the reactions, because that is what he has asked. So how are we going to find out the reactions? Means this is a formula. Reactions is nothing but K into Q minus F. So how am I going to find out? Again, we need to go with the matrix? No, not necessary. See, whichever the row you have completely deleted. Okay, so look at this row. So you have deleted this row. Now what you need to do is, from the stiffness matrix, whichever the row you have deleted, multiply with the respective displacements. Okay, see, this row multiplied with this displacements minus the respective force. So if I have done that, So 1.512 into Q1 plus 0.384 into Q2. See, 0.384 into Q2 minus 1 into Q3. I think it's minus 1. Minus 1. Yeah, it's minus 1. Sorry. So this becomes a minus Q3, and 0 into Q4, 0.512 into Q5, minus 0.384 into Q6, minus whatever the force which is acting in the first row, that force will be substituted here. Okay, in the same way, the second, whichever the eliminated second row and the fourth row, I have written with the values over here, and look at the forces at 1, 2 and 4, the forces are 0, 0, 0, 0. So when you substitute all the values, see, we have already taken Q1 as 0, so obviously anything multiplied with 0 will be 10 to 0. Q2 is also 0, Q4 is also 0. So wherever Q1, Q2 and Q4, okay, Q4, Q1, Q2, because we have assumed by elimination technique Q1, Q2, Q4 is 0, so that will be reduced. And meanwhile, look at the answers. Q3 is also 0, so any thing associated with Q3 is also 0. Okay, if you do the simplification, you're going to get the value of R1. So if you substitute the value of Q5 as 4.619 and Q6 as minus 2.349, you're going to get the answer as minus 14.629 kilonewton. This is your R1 value. Similarly, when you substitute Q5 and Q6 values over here, R2 I've obtained minus 10.971 kilonewton, and R4 I have obtained as 31.241 kilonewton. Just check it out, check the answers. Okay, so this is how we are going to find out the reactions. Okay, so by this I think I'm going to wind up my trusses, and I'm going to start with the beams. Okay, yeah.